Uh, Now we are proceeding for another talk on Skydive, analyzing topology and flows in OVS-DPDK and OVN OVS-DPDK environments. This talk will be given by Team Red Hat from Mr. Masco, Mr. Newman, and Mr. Yoganathan. Mr. Masco possesses 5 years of experience in OpenStack development and currently is one of the co-inventors of the Skydive. Newman is a software engineer in Red Hat, Bangalore, and he contributes primarily to OVN, part of Open vSwitch, and OpenStack Neutron. He has also contributed to OpenStack OOO in integrating OVN services. Before contributing to OVN, he was working on Open Control SDN solutions. So let's put our hands together and invite on stage Team Red Hat.
Thank you, everyone. So let's start this session talking about Skydive. Throughout the day, we were talking mainly about DPDK and the lower level services. So now let's go a level up in the stack, and see how Skydive comes into picture and how OVN comes into picture. So before talking about Skydive, I would like to just talk a little bit about OVN, what is OVN, and just brief about the architecture of it, and then my friends will take over. Okay, so let me just talk about OVN. So Open Virtual Network, it's actually a part of Open vSwitch community project. It provides layer 2 and layer 3 virtual services which uses Open vSwitch internally. It has a native services as well, like DHCP. It has internal DNS support and IPv6 support. So if we just see OVN, how it fits in, it talks to the OVS. I would like to take OpenStack as an example and see how how OVN fits into it. So I think everyone knows, hopefully everyone knows OpenStack and OpenStack Neutron. So when we talk about OpenStack, we would assume we'll be having a data center. We will be having various compute nodes. On each compute nodes, the primary goal is obviously to spawn your VMs or containers. And if we so these slides talk about what we have in the Neutron reference implementation. So we have a Neutron server at the top, and we have various ML to OVS driver and various Neutron agents which provides the virtual solutions. So basically all these Neutron agents like OVS agent, L3 agent, they provide layer 2 services like switching and routing. So basically in an OpenStack environment, you will have your VMs which will have virtual networks created, right? And all your VM will be communicating to each other. And if you want your VMs in one network talk to other VMs, you will hook up a virtual router. And if you want your VMs to have a upstream connectivity, so you would hook the router to a gateway. So now let's compare that with how OVN comes into and how it integrates with OpenStack Neutron. So at the top, again, we have a Neutron server over there, and we have an OVN driver, which is part of Neutron server. And we have various OVN services like OVN NorthD, OVN controller, and OVN DBs. So OVN DBs and OVN NorthD, those are the services, they run in the controller node, and OVN controller is a service it will be running on each compute node. And OVN controller will be talking to Open vSwitch internally. So we do not have agents like how we have in reference Neutron implementation. So we don't use namespaces to provide the virtualing, to support layer 2 and layer 3 services. Okay, so let's see how OVN works. So basically, our Neutron server, we have a ML2 driver, OVN, which is called networking OVN. It talks to a database called OVN northbound database. And we have a service which is OVN NorthD, and we have a southbound database. So these three components, like they run in a, you would normally run in a controller node. And so these OVN northbound and southbound database, they are nothing but OVS-DB servers. Like if you are familiar with OVS, you would know that there is a OVS-DB server process running with conf.db, right? When you create a bridge, a port, all that information is stored. So even in the case of OVN, we use the same OVS-DB server, but we have our own database with various tables. So when we talk about virtual networking, right, like OpenStack, we'll have a virtual network, virtual port. So all those things are stored in the OVN northbound database. Like you have a neutron network. Similarly, the networking OVN driver will write it into the OVN northbound database. So when OVN northd comes to know that there is something written in the OVN northbound database, it reads that, converts those northbound entities into OVN southbound entities, which are nothing but logical flows. And it also has information about the port binding and, yeah. So each OVN controller here, as you can see, it's running on each hypervisor, connects to the southbound database, and that's how it comes. So this OVN controller will get to know all the logical flows, and it internally programs the OVS flows, depending on the state of the, depending on how VM has come up in a hypervisor or not. So let's see how it works as an example. Again, the same. We have a networking server, right? So you would create a OpenStack. You create a network. So when you create an OpenStack network, the OVN ML2 driver will write it to the logical switch northbound database called logical switch. You are seeing it's almost similar entry here. And when you create ports, like you create a subnet, and when you create a port, you would see here that it is written into the OVN northbound database. There's something called switch, and there are something called logical ports. So it's just a representation. So when OVN northd sees that, it converts that into logical flows. Few things to remember is, in the case of southbound database, there are two tables. One is a chassis table and one is a port binding table. Chassis table is nothing but all your hypervisors connected to the southbound database, like right, OVN controller connects to the southbound database, so that is registered in the chassis column. So it shows how many hypervisors are connected, and for every logical port you connect, like a neutron port, so there is a corresponding port binding table, which is maintained in the southbound database, and it has a state saying that where this particular port is hosted on. So right now we just created two ports. They are just ports, right? As you can see, the chassis column is empty. So when you create a VM associating this neutron port, that's when OVN controller will come to know that a VM is connected with this logical port, and it programs. So basically, OVN controller has a concept called logical flows. I think we are all familiar with Open vSwitch OVS flows, where you have match and actions, right? And it is very, very specific to each compute host. Either an application or any controller communicating to the vSwitch will program those flows. But whereas logical flows, they are very much similar to OpenFlow flows, but they are expressed as logical entities. You do not say, at that point of time, since OVN northd generates these logical flows, it doesn't know where that port is connected to in the system. It just generates logical flows. When you see these logical flows, it's quite straightforward. It says if the packet is coming from this input here you would refer to as the port name or the logical switch port name. So it is all expressed as logical entities. At this point of time, I mean, it's just an entry in the database. So when actually, when a VM actually gets hooked up, that's when it is programmed. Okay, I mean, so this is an example whereas how a packet in the same host is delivered in the case of OVN. So in the case of OVN, like we have logical pipelines, ingress pipeline and egress pipeline. So when the packet comes in from a VM, it first enters the ingress pipeline, and we have various tables what needs to be done, and finally it enters to the egress pipeline, And by that time, a decision, OVN controller would have programmed the flows, which makes a decision basically where the packets needs to be delivered. Oh, sorry. If the two VMs, let's say they are in a different host, then the packet will go via Geneve tunnel. So in the case of OVN, we use Geneve tunnel for the encapsulation, primarily because we can store metadata in it. So this is just a representation of logical flows and how they look, and we have a utility called OVN trace, which we can use to inspect the logical flows, even without knowing the actual physical state. So just skip to this. So as I said, OVN controller will generate the physical flows and program it. Yeah, so as I mentioned earlier, OVN controller will watch. So basically, OVN controller will be monitoring your integration bridge as, like, let's say OpenStack Nova boots a VM, it knows about that and it programs the flows. Okay, so this is just an example, like, instead of creating a VM, I've created a namespace here and attached a port to the OVS bridge. And you can see the external IDs column there. There we see the logical port name, and that's how OVN controller will figure out that this particular interface is connected to a logical port, and it programs. Okay. If you see these columns here, port binding, so this reflects where that particular port is bound, on which compute host. So that's how each OVN controller would come to know that this VM is residing on which chassis. So even when it takes a routing decision, it just sends it to the destination hypervisor. It's like it just sends. Okay. So this is just an example showing that how the ping would happen. So if we want OVN to work with OVS-DPDK, it is quite straightforward. You just need to do like how you do with OVS-DPDK, like program, configure all those OVS-DB parameters, and it just works straight away. So nothing special has to be done for OVN to work with OVS-DPDK, so it works. Okay, I think now we'll talk about Skydive.
Hello, thanks, Norman. Now myself Moscow. Now we're going to see about the Skydive network topology and flow analyzer tool. Before we look into the Skydive concept, first we'll see why Skydive. As all we know, the SDN is very complex. It's a little bit difficult to learn itself. So then how it will be to troubleshooting. So we all went into the phase. And then it's very highly dynamic. It's changing the tables and everything changing very frequently. And we don't have very enough tools as a open source tools to troubleshoot the SDN infrastructure. So we started the Skydive with specific goals that it should be the SDN independent, so it should support every SDN, and it should be able to analyze the network framework in real time, as well as we can able to do the post-mortem, and it should be like each and every software. It should be lightweight and easy to deploy, and yes, as Skydive is a single binary. So if we see majorly Skydive, we can define the Skydive components in two parts. One is agent, another one is analyzer. Mainly agent, it will collect the topology information and flow information and send it to the analyzer. And analyzer will segregate and store all the information in the storage backend. And as it is a front end, it will serve the API for the applications and REST UIs. So this is the high-level architecture diagram of the Skydive. Skydive mainly depends on the event-based graph engine. So as it is event-based, you can get each and every modification notified to your analyzer. So the agent will collect all the information from the topology probes. So it will run the listener, and it will give the network modification to the graph engine, and the forwarder will give to the analyzer. Analyzer will store into the storage backend, currently we are using Elasticsearch and OVN-DB as a backend storage backends. And we have a flow table. Flow table will get the flow information from the flow probes, and it will send to the analyzer. Analyzer have the flow enhancer. So the flow enhancer, what it will do, it will don't dump the just as the packets. It will along work with the graph engine, and it will add some extra information like where the flow is started and where the flow is ending, and in which node we capture the flow. It will add all the such kind of information, and it will store into the storage. And then we have on-demand probes. So what it will do, it will listen for the etcd event. So whenever we are creating the flow capture or something from the API, so we'll get the etcd event. So after getting the etcd event, it will work with the graph engine, and it will find out what are the nodes we need to start the captures, and it will start the capture on each nodes. And we have a Gremlin engine to get the all the topology nodes and flow information. We are using Gremlin query. So the Gremlin engine will parse the Gremlin language, and it will give appropriate data to the APIs. We'll see a little bit more about the topology probes. So topology probes, currently we are supporting OVS-DB, Netlink, NetNS, all those things. So we will get the info, we will hook into the OVS-DB, and each and every modification we are running the listener, and we will get the events from the listener, and we will store it into, and we will give it to the graph engine. And for the SDN, we have the different connectors for each SDN. This is how we are achieving the SDN independence. So for each SDN, if you want to support your own SDN, you have to just write a connector here. That's it. Then you can use the Skydive for your SDN. So these connectors will just it's nothing a big deal. So you just need to give the SDN specific information only and give it to the graph engine. So graph engine will use that, and we can get the information. And we'll see the topology query. So the graph engine, to form the graph, it will use two components. One is nodes and another one is links. So nodes mapped into the interfaces and network objects with some useful metadata. All those things will be mapped into the nodes. And L2, L3 ownerships links will be mapped into the links. And it is, as I said, it is event based. So you can get all the events to the agents, and even web UI also you will get real-time events. And yeah, Gremlin query we are using to get the topology informations, and we are storing the full history of the topology. So at any time you can go back and you can get the status of your topology status. So currently we are using Elasticsearch and OVN-DB as a backend. So this is the sample query. So what this query does, it will, if you run this query, you will get all the OVS bridge which don't have the name as br-end. So it will return rest of all the br in. So you will get the topology diagram. So you will get all the information like a host name, and you will get metadata, what is the MAC ID and name of the bridge. Like similarly, you can get, even now we are adding a routing table and neighbors, everything you can get. So next we will look into the flows. What we call flow mostly means what it contains. It will contain the layer information. Currently we have link layer, network layer, transport layer informations will be added into the flow. And metrics, we are giving both packet count and bytes. And we can have the source where the flow started and where the flow is ending and where the flow is capturing. And we'll get the tracking ID, L2 tracking, L3 tracking IDs, and encapsulation support. So you can get the sub packets also you can get. So we are supporting currently VXLAN, GRE, all those things. And to start the flow, you need to just create a capture. So again, that is Gremlin query based. So you can just send the Skydive API query, and the on-demand probe will listen and start the capture on all the nodes. And currently we are supporting SFlow, AF packets, OVS mirror, ePPF and DPDK flow types and all currently we are supporting. And traffic is captured at the agent side, and it will be sent to the analyzer. So in the flow will be saved sometime in the agent. So we can configure that in the config file. So after that, the flow will be expired in the agent, but it will be stored in the memory backend. And we have the BPF filter for all the captures, so we can reduce the flow junk. So no need to capture all the packets. So we can look into the specific flow what we want. So we are supporting in the standard BPF format. And as I said, it's stored into the local flow table, and it's sent to the metrics, and we can map the endpoints, interfaces, everything, and store into databases. And still we are using the same Gremlin query. So we can use the Gremlin query, we can retrieve the flows. Similarly, I said we can, these are some example queries. So first one will give based on the tracking ID, we can get all the flows. Next one, we'll get all the flows which the flow is started from that particular IP. And next, last 1 hour, in the particular BR int node, how many flows I have, like that you can write the Gremlin query and get it. And some of the attractive features, other than this, what are some attractive features what Skydive has is, one is alert mechanism. So you can, for this in the example alert, you can set the ETH0 port whenever it's going to shut down, you can get the alert message. So you can look into that. So like that you can lively, you can monitor the nodes, and you can, for a particular link, if the bandwidth is going some above that level, you can get the alert message. Like that you can set the alerts. And we have the traffic generator. So you can generate the traffic between, to check the connectivity or something, you can generate traffic between one node to another node. Currently we are supporting ICMP, TCP, and UDP formats. And we have a Python client, so you can use it in your Python software to query the Skydive information and use it the Skydive. And we are supporting high availability, means, so I said analyzer, right? So we can have multiple analyzer. So whenever one analyzer goes down, you can get another analyzer will become act as a master, so it will serve. So you won't be disconnected when some analyzer is getting disturbed. So we can see some demo with using the OVS DPDK environment. So this demo will be presented by Mr. Yogi.
Could you start there? Yeah. So let's have a quick look at the Skydive interface, so you can start playing with it. So I did like a quick introduction to the how to use the Skydive interface. So this is a simple topology map. Maybe in your network, real network, you might have hundreds of nodes. So it might be quite overwhelming when you have hundreds of nodes. So you can use the same Gremlin filters at the top to filter on the number of nodes. So you don't have, so easy to select your nodes. I'm going to select all the BR int. So the same set of Gremlin queries can be used for capturing the packets, for packet injection, for even checking the topology, setting up alerts. So you can use the same set of Gremlin queries, and it supports regex expression. Here, this is an OpenStack environment. So yes, we have agents. He'll be showcasing agents for namespace and OVS-DB, but not Docker, since it doesn't have a Docker interface. So here you can see the names. Since the namespace probes shows you all the namespace that's present in your OpenStack environment, and netlink, you can find the statistics of the different netlink interfaces. And OVS bridge, OVS-DB probes gives you the OVS bridges. And each of the nodes have metadata information. So you'll be using those metadata information in your Gremlin queries to search your nodes, and using those metadata information, you'll be, it'll make navigating or Skydive a bit easier. So let's say you want to capture packets. So let's capture on a package on OVS bridge. So before DPDK support, DPDK support, it means capturing on an OVS port, DPDK port connected to OVS. The only way to capture, analyze packet using Skydive was using just the flows in the OVS. So here is just an example. So of how you can use the flows in the OVS S flows to analyze the packet loss here. So here on the right-hand side, you can see the AB and BA, that's the back and forth traffic. the packet is coming only one way, the other way the packets are missing here. So I mean, maybe it's a issue the firewall rules. After fixing the firewall rules, you can say that the packet is going both ways. But if you want to fine tune further and you want to isolate a particular DPDK node, we can use a OVS port mirroring feature. So at present, we thought of using on a quicker way, we thought of using a port mirroring feature for OVS to capture packets on OVS on a DPDK ports. Maybe in the future implementation, maybe we can use DPDK pdump packets. So that's the other pdump. That's the other option to implement in Skydive. So here we are capturing on the mirror ports, and we are creating the mirror ports here. After creating the mirror ports, just a second. We'll start up again a packet transfer, and it will be reflected in the packet capture of that mirror port. So here at present, these examples were all based on when you are transferring packet from a VM to VM. In an enterprise environment, you might not have access to a VM. So Skydive also has a packet injector, so you don't need to actually have a VM. So you go here, in this example, I'm creating a generated packet from one of the namespace. So you can use the DSCP namespace for initiate a packet, and you can capture it in the same mirror port. So that's one of the advantage. So if in case you don't have access to your VM or the VNF, you can generate packet using Skydive for any of the namespaces or any interface, and you can capture the packets here. The last flow tables gives all the flows. If you have multiple capture running, it gives all the flows. And or you can check each of the individual flows to get the details. And it has a command line interface also. So if you want also you want to automate it, you want to use triggers, you can start the packet injection here, and you can query the capture point. So if you have multiple capture points, you can query the capture point and get the statistics of the package. And if you have multiple capture points, you can see the packets that were transferred across different package points and compare if there is a miss in the packet, and see you can really zone down on which of the node or port where the package is missing. So that's the point of using Skydive.
We are open for questions.
DK fetch for you in this case. So by DPDK, I can always capture the packets. So I can guess the interfaces you were using for capturing or generating. That is still possible for a DPDK-like engine. What about the other stats? Are you fetching it from DPDK?
Oh, no.
Stats like packet in and out?
So Skydive initially was support only to kernel stack. So by using at present so in an OpenStack environment, in an NFV, we will be using both a kernel-based stack, OVS stack, and a DPDK stack. So we're adding at present to handle capture packets for a DPDK-based OpenStack. With our at present solution is to use OVS port mirroring. So using Skydive now, we are able to capture both a kernel-based stack, where we have OVS and OVS DPDK packets.
So if I understand correctly, you are using port mirroring, and you will mirror a port and then fetch packets using DPDK across that port, irrespective of how the original port is being used.
For DPDK port, we will be using port mirroring. Other option is DPDK pdump. So since that is not done, we are using this option. For kernel stack, you can use pcap libs or even so there are multiple options for kernel-based stack. So for DPDK DPDK for capturing packets on a DPDK port, other than DPDK pdump, it might be difficult to capture packets. So so we opted for this way. So if you want to analyze the flows, packet of flows, we'll be starting capture point across different nodes. So there's if you want to capture or start a capture across two different nodes, there's a shortest path algorithm in Skydive. So okay, you just have to select two different points in the in your in the environment, and it will start the capture across all the nodes. So it will start on your bridges and the ports in between and the Ethernet interface. So after starting the capture, you can collect the data and you can compare the flow details and see where the loss has occurred.
Thanks.
Yeah.
Hey, hi. I have two queries. The first one was part of the presentation in which you gave the small dump or overview of the structure. So can we go to the slide deck, please? Yeah. So you showed me the database, the southbound database, and the northbound part, and different controllers getting this one. Here, I have only one query here. You mentioned that you have the environment 1, 2, 3 on the bottom side. So the southbound database that is having, is it dumping all the flows, or it is specific to that node 1, node 2, or node n?
So southbound database will have all the dump of all the logical flows for the whole system.
It's not for the particular controller.
No, not for the particular controller. So it's like defined, logically for this data path. I mean, the flows would look like if the import is equal to port 1. You can use the name port 1. Let's say you created a neutron port by the name port 1 or with a UUID, right? It would be expressed that if import is equal to this, and if it's a, let's say, a DHCP packet, send it to controller.
Correct.
So when OVN control, how that translates to OVS flows is we make use of the registers, okay?
That is okay. My problem is not there, because after showing this figure, you then showed me how the OVN ports are created, a chassis is assigned, and how a VM gets assigned to it in your part.
This one?
I believe so, yes. So I was under the assumption or understanding that when you said the southbound database, it is for those chassis ports only. But right now you mentioned it is for the complete flows. That means irrespective of the chassis, every chassis and ports would be there on each and every node, is what you're saying. Am I right? Okay, let me rephrase.
Can you rephrase? Yeah.
Yeah. You have chassis.
Okay.
You have 5 ports or n number of ports on each chassis.
Okay.
That is your VM1, VM2, VM3 node instance.
Okay.
Now let's go back to the figure.
Okay.
Yeah. So the question is, the southbound database, is it per chassis that goes to the controller, or is it for the complete flows what you have?
It's for the complete flows.
Why not for the particular chassis?
No, see, OVN North D is a service which is running at a very high level.
That's
so
your
North D is the service which generates the logical flows looking into the northbound database, okay? I mean, whenever you create logical switch port, logical switch neutron network port, it gets stored in northbound database.
Yes.
So OVN North D looks into that and it converts into logical flows.
Correct. In your northbound database, don't you add flows per chassis, or is it overall? If it is per chassis, then it would be available also in the southbound database. So that is where I'm getting confused.
Okay, probably let's take it offline and I'll clear up your question.
And the second presentation, in that there was mention about the DPDK flow analysis and capture. But I think half of it was taken up. So I would like to understand the other half of it. You guys mentioned you're not using PDUM because earlier version was not working with PDUM or something like that? So in OVS, you're creating a mirror port, and if n number of packets are coming on the mirror port, it is mirrored to the mirror port, and using normal TCP dump or any analyzer, you're doing it. Now my question is, there is application like NetStat and all, which is standalone open source stuff, which you can, it's a lightweight stuff, which you can integrate with DPDK, OVS, or any other stuff, which can analyze and tell you what kind of traffic came from different ports, what are the current stats of it. Why not use that, and why did we go for this type of port mirrored then copy and tell? Because NetStat is inline, and this is more like offline, where you create a mirrored packet, then analyze it. So it is more computation, more memory. The other one, it's a complete inline stuff. So that's all.
Okay. Yeah, we can discuss on that.
Maybe the Skydive developers can take a look.
Yeah, it's also, I mean, I'm not sure. I explore that option. I'm not sure. I mean, I'm not sure it's a DPDK. I guess it is. So we'll explore that option. Yeah. Yeah.
We'll take one last question, please.
one very quick question. Is this by any chance open source?
Yeah.
Yes, everything is
The
open
whole
source.
of it?
Yeah, it's
Yes.
yeah.
Okay, so it's like the whole UI as well is
Yeah.
supposed to be in open source. Okay, thanks.
Everything.
Thank you so much, Team Red Hat. Indeed, it was an informative session. Thank you so much once again.